SwayamPrabha. Digital India. Educated India.
Today, in this third lecture of this series, we will look at some of the jet engines that have developed over a period of last 60 years and have powered various kinds of aircraft flying around the world. This is generally referred to as jet propulsion. The basic concept of jet propulsion comes from the simple concept or idea that if you have a device in which a certain amount of working fluid, and in our case this working fluid is almost invariably air, and as a result of which all jet propulsion devices that we are talking about are essentially air breathing engines. These air breathing engines have a propulsive method by which this is illustrated in this picture. In this method, the air is inducted into a propulsive device, and this working medium is then accelerated through the device, and the air is exited from the device with slightly higher velocity. As a result of this, the working medium actually acquires a change of momentum. This change of momentum is what finally manifests itself in the form of force, or more specifically the action of the exhaust jet from the propulsive device creates the reaction, which is the propulsive force, or what we would more specifically be always referring to it from now onwards as thrust. The thrust is a result essentially, or a reaction to the change of momentum that occurs across the propulsive device. This is the basic understanding on which all propulsive devices that we are looking at today would be essentially based on. Now, this requires that the air, which is again our working medium, going into the propulsive device has certain properties in terms of pressure, temperature and velocity. It goes out with another set of properties, again another set of pressure, temperature and velocity, and a change of these properties is what produces the change of momentum. Now, basically the change of momentum that we are looking at refers to the change of velocity. Velocity, as you know, has a magnitude and a direction, and the direction is as shown in this picture in the same line. That means, the incoming velocity and the outgoing velocity are exactly in the same line, and as a result of which the action of the exhaust velocity and the reaction produces a thrust in the same line in which the velocities have come in and gone out, and as a result of which a thrust is produced in the line of action of the production of exhaust velocity or exhaust jet more specifically. Now, as you can see in this picture here, the flow goes out with a certain pressure, which is more specifically a static pressure, and this pressure, if we call it, let us say P e as the P exit pressure, may be equivalent or may be different from the pressure that is existing outside in the atmosphere, which we refer to, let us say, as P a. Now, in this particular instance, at this moment, we are considering that the pressure exit pressure has indeed reached the atmospheric pressure P A by the time it exhausts from the propulsive device, as a result of which at the face marked E, at that particular station, the difference between the two pressures is 0, and hence what we get a thrust dependent only on the change of momentum, and is often referred to simply as the momentum thrust. Now, this is a very ideal condition. We shall see later on, just a little later today, that in case your exit pressure P E happens to be different from the atmospheric pressure P A, we would have a thrust value which would look somewhat different from what we are looking at right now. We will come to that in a few minutes. Let us look at a real propulsive device. What we had just looked at is an ideal concept of a propulsive device. If we look at a real propulsive device, or what more specifically can be called a gas turbine based turbojet engine, we have number of components here. We have, as usual, the air coming in. We have the air coming in from this end, that is often referred to as the intake, and this component here is a common element in all kinds of jet engines, that you have to have some kind of an intake. At some point of time later on, maybe we will discuss the importance of this intake, and then the flow goes through a process of compression through a compressor. So, this is a compressor, and in which the flow actually gets compressed, or the pressure actually goes up, and then we have a combustion chamber in which the flow actually acquires burning fuel. So, the fuel is burned into the air, and a mixture of burned fuel and air then is passed on to the turbine. The turbine extracts work from this hot and compressed air or gas, and part of the work that it extracts is now passed on through the shaft onto the compressor. So, the turbine takes out certain amount of energy in the form of work and runs the compressor, and compressor does the compression, passes on to the combustion chamber. So, there is a energy loop here. So, through the turbine and compressor, certain amount of energy is continuously looping. This is necessary for sustenance of this engine. So, certain amount of energy that is actually in the gas over here is used to continuously sustain this loop. Balance of the energy that is available now, which is hot and which still has sufficient amount of pressure, is now passed on through a various kind of ducting system, and then finally through a jet nozzle, which then exhausts the flow in a jet with a high velocity. Now, the engine that is shown here, you can see here an element called afterburner. We will probably have a chance to discuss the details of this a little later. As the name suggests, you have another round of fuel burning over here, and the temperature of the gas, this gas may be raised to even higher values, and then only it is exhausted through the nozzle, and as a result of which quite often you end up getting a higher amount of thrust. So, these are additional options that some of the jet engines have, not all the jet engines. Many of the jet engines do not have any afterburner. So, this is an optional item. Quite often it is used during for the military aircraft engines, and most of the civil aircraft engines do not have any kind of afterburner. So, this is a kind of a sketch or a layout of a real engine, in which it passes through various components. Let us go through them quickly again. You have a compressor, you have a combustion chamber, which actually burns the fuel and inputs the energy from outside, and then you have the turbine, and then it goes through a jet pipe and then through exhaust nozzle, at the end of which you have a net increase of velocity and more specifically net increase of momentum of the air that has come in. As you can see, once the air comes in through the intake, it has nowhere else to go. It has to go through all the components and exit through the nozzle. It has nowhere else to go. So, the amount of air or the mass of air that comes in here would be approximately same. With the addition of fuel, there will be a little more that exists finally from the propulsive device, that is through the nozzle, and that produces the change of momentum, and this change of momentum produces the action, which of course, as we have discussed, produces the reaction which creates a thrust. So, this is the process through which a real engine actually operates. We shall be talking about these processes more and more as we go along. The understanding now that we have from the previous diagram and from the present diagram is that a certain amount of air mass is captured, it is processed through various processes, and then it's exhausted in a jet at a higher velocity with a higher momentum, and that creates a thrust. Now, this is the understanding with which we have based our idea that the thrust can be created through the action reaction process. It is easier to understand it that way. It is easier to put it in simple mathematical form, as we can see here. You can write down the thrust equation here based on the mass flow as we are talking about, and the change of velocity from intake velocity or air velocity to the exit velocity, and that gives you fairly accurate mathematical estimate of the thrust that may be produced by the propulsive device, and in this particular case a particular engine. However, the actual thrust production of a real engine often happens in a slightly different way. Conceptual basis of change of momentum, as I mentioned, is the easier way of understanding. However, actual method by which the thrust is produced is slightly more intricate. Let us go through again a sketch which is a representative of a real engine. We have airflow again coming through an intake. We have a compressor over here through which the flow undergoes a certain amount of compression. So, at the end of the compression process, this air actually has a very high pressure at this point. So, at this station the air has very high pressure for the same mass. Now, simple fluid statics will tell you that if air or any fluid has a higher pressure at this station, it will exert a pressure or a force across this body from this side to that side, and that is what is shown here. So, at the end of the compression process, the entire body of the compressor, which is a solid mass actually made of blades, would experience forward force, which is shown by the arrow over here. And then the air actually goes through a process of combustion, in which the fuel is burnt, inside which the air undergoes again some change in temperature, some change in pressure. As a result of this change of temperature and pressure at the station over here, it is very likely now that the air or the gas at this moment with the burnt fuel would have pressure and temperature that are quite different from the pressure and temperature that came in over here. Now, the collective pressure that can be integrated over this surface, let us say, can give you pressure that is a net pressure that may be acting in the forward direction, that may jolly well be acting in the backward direction too. So, the combustion chamber here, if you integrate the pressure over the entire surface of the combustion chamber, you would probably get a net pressure acting over this entire volume, which could be in the forward direction or it could actually be in the backward direction. And then of course, the air is exited to the turbine, which does the work and which supplies to the shaft work to the compressor. Now, this turbine, through the turbine, what happens is the work is extracted. As a result of extraction of the work, the air actually loses certain amount of temperature and pressure. So, the pressure at this end of the turbine is substantially lower than the pressure at this end, at the forward end. So, the air mass actually exerts, again from fluid statics, the air mass would exert a certain amount of pressure through the body of the turbine, and that exertion of pressure or force, a net pressure over the entire area would be a force, and that would be in the backward direction. So, the turbine essentially produces a backward force while operating inside an engine. Now, as the flow is exited from the turbine with the remainder of temperature and pressure, it passes through a jet pipe and then it passes through a nozzle, and it exits from the entire propulsion device or engine over here, and in the process it of course has pressure over here, which is quite different from the pressure over here, and one can very well imagine that the pressure over here would be substantially less than the pressure over here. So, this difference of static pressure, again from fluid statics, is most likely to create a pressure field, which net pressure of which would be acting in the backward direction. Now, as a result of this, the net of all these forces, if you take, you have a certain amount of force that is acting in the forward direction, which we could call forward thrust, and there is a certain amount of force which is acting in the backward direction, which we would call probably rearward thrust. And the net of the two is what we would call net thrust. So, as you can see here in this diagram, all the components that are part of the engine actually participate in the process of creation of thrust. And our understanding that the momentum difference between here and the end station, last station here, gives the thrust is essentially a concept. It is a very handy and convenient way of estimating the thrust, quite often reasonably accurate. However, a more accurate and more detailed measurement or estimate of thrust can be obtained only after we have all these components rather accurately determined, and the final value of the net thrust from here should be pretty close to the estimate that we had made earlier on the basis of net change of momentum. So, this is the mechanism by which the thrust is actually created inside a jet propulsion device. Let us now look at the equation that we were talking about, the thrust equation. We had seen the first part, which constituted what we had called the momentum thrust. The first part of the momentum thrust can be called the gross momentum thrust, which is the action reaction principle at the exit of the propulsive device or the engine. This is normally the component which is produced by the incoming flow, and this is often referred to as the intake ram drag. So, the difference of the two is the net thrust that is normally produced by any propulsive device because of the change of momentum. So, this is the incoming momentum, this is the outgoing momentum, and the difference of the two is the net momentum thrust. Now, as I mentioned in the earlier diagram, if you can quickly go back, the pressure over here need not always be same as the atmospheric pressure or the ambient pressure that is existing in the atmosphere. If the pressures are different, and in many operating conditions of the engine, it is entirely possible that this pressure would not be same as this pressure. As a result of this difference, if it is a positive difference, the area at the exit of the engine or the propulsive device multiplied by the difference in the pressure gives you a force, and this is what we call pressure thrust. Now, this pressure thrust normally then comes into existence when the net pressure at the exit phase is not equal to the atmospheric pressure. Now, from this equation, it would seem that this is some kind of a additional thrust that is coming into picture. One needs to understand that this pressure thrust actually appears when this velocity, the exit velocity, is not at its maximum, and a remainder of the energy, kinetic energy, that is being produced through these propulsive device appears as a thrust, as a pressure, and gives you pressure thrust. So, the momentum here at the exit would be a little less than the maximum, and as a result you get a little less of the momentum thrust, but you get a little of the pressure thrust. And quite often, if you quantify the values, you would probably find that the total thrust inclusive of the pressure thrust would actually be a little less than the maximum momentum thrust that you can get when the exit pressure is equal to the atmospheric pressure. And this is when the flow is said to have completely expanded through the nozzle. That means, the nozzle has completely used up all the kinetic energy that is available, all the energy that is available into velocity, into kinetic energy, all the potential energy that is available into kinetic energy, and as a result of which the pressure over here now equals to the atmospheric pressure. Now, the engine designer has to be very careful in designing the nozzle to ensure that under no operating condition the exit pressure P e should be less than the atmospheric pressure P a, because if that happens, we are going to have a negative component over here, and we are actually going to get a negative thrust. Now, that is obviously not a very desirable thing to happen, and as a result of which it is necessary that the engine design, specifically the nozzle design, is made such that under all operating condition, a pressure thrust that is produced is either positive or 0, but never negative. Quite often the engine designers try to keep a small margin, and as a result of which you always get a small pressure thrust, but never a negative pressure thrust. The other parameter which often defines the action of a propulsive device is simply referred to as propulsive efficiency. Now, propulsive efficiency, which we had a look at in the previous lecture, can be formally defined now as a ratio of the useful propulsive energy that is available at the end of the propulsive process to the thrust power that is produced. Okay? And that, if you take the ratio to that of the energy that is used and unused kinetic energy of the jet. Now, when the jet is going out of the propulsive device, a certain amount of energy is spent through the process of the exhaust process, and this kinetic energy is a lost cause. And as a result of this, a large amount of energy in the form of kinetic energy is exiting the propulsive device without getting any work done out of it. Now, that, as I mentioned, is a lost cause. So, propulsive efficiency tries to capture how much of the energy that is available at the end of the propulsive process, that is the useful propulsive energy, and how much of that is used, and how much of it has actually been left unused, and a ratio of these two finally gives you the propulsive efficiency. Just to explain that the kinetic energy that is going out of the jet, this is often referred to as the kinetic energy relative to the earth, which with reference to the moving aircraft is considered a stationary body. So, the formal definition of the propulsive efficiency can now be written down as, this is the thrust power, which we have written down here, okay, and thrust being now expressed in terms of power, and this is the energy that is available. So, this is again the thrust power, and this is the energy with which the flow is going out of the entire propulsive device, and this energy will not be available for any propulsive purpose anymore once it exits the propulsive body. And simpler derivative of this full form appears in the form, very simple form over here. As you can see here, the propulsive efficiency is thus dependent solely on the ratio between the exit velocity and the entry velocity of the working medium, that is air, and that clearly gives us a quick and handy idea what is the efficiency with which this propulsive device is most likely to work. Now, the fallout of this very simple propulsive efficiency definition actually tells us a few stories. Let us see what actually can be extracted from this very simple definition of propulsive efficiency. If, for example, your exit velocity is rather large compared to the entry velocity of the air, that means a very large change of velocity or a large amount of acceleration has occurred through the propulsive device, and quite often that happens with a rather low mass flow. You could get a reasonably good amount of thrust produced, but in such a case the propulsive efficiency is going to be low, because this ratio is now rather big, and the denominator here is going to be much higher than the numerator, which is 2, and the propulsive efficiency thus would come out to be somewhat on the lower value. And this is typical of a jet engine, in which normally a large exhaust velocity is observed, and a jet engine operates with a comparatively low mass flow, but still produces a reasonably good amount of thrust, and that is why the jet engines are so attractive. They are compact and small, produce a large amount of necessary thrust. However, we have to keep an eye on the fact their propulsive efficiency is not actually very high. They make compact thrusters, but they are not very high in propulsive efficiency, and we shall see later on that this propulsive efficiency does have an impact on the fuel efficiency that everybody is so concerned with. The other end of the picture is, supposing when the exit velocity is equal to, or let us say almost equal to, the entry velocity V A, then the definition tells us that numerator will be equal to the denominator, both would be 2, and as a result of which your propulsive efficiency is actually going to be 100% or very close to 100%. However, if that happens from the earlier equation over here, assuming that this pressure thrust is 0, the thrust produced would actually be pretty close to 0. That means, when the propulsive efficiency is 100%, the thrust produced would be 0. Obviously, such an engine is of no use to us. The solution is that if you have a very small change in the velocity, which operates on a very high mass flow, then a substantial amount of thrust can be produced. So, we now turn our attention to the mass flow and not the change of velocity. And if we can have a propulsive device when the operative mass flow is very high, in such a case you can produce a requisite amount of thrust, a substantial amount of thrust, and that thrust production, mind you, now is going to be with very high propulsive efficiency. Now, this is obviously a very desirable phenomenon, where your fuel efficiency is going to be quite good, and this is the kind of engine that normally we can see in propellers. When we operate with propellers, propellers typically operate with low acceleration, operate with very high mass flow, and operate with very high propulsive efficiency. And if you have a turbofan, which is a normal jet engine these days, a large part of the thrust is produced this way. That means, with a very large mass of air going through a very small change in velocity, working with very high propulsive efficiency, and comparatively small part of the thrust is produced by the jet effect, which has a large change in velocity and operates with a comparatively smaller propulsive efficiency. So, combination of these two is what we see today in the form of turbofans, and a judicious mix of the two would give you a overall propulsive efficiency, which would be quite good. This graph here now tries to capture the various kinds of propulsive efficiency variations with flight Mach number for various kinds of engines or propulsive devices. If you look at this graph now, the turboprop engine, which as I mentioned operates with a high mass flow and a small change in momentum, operates with a high propulsive efficiency almost through its entire operating range, and somewhere over here it starts dropping when the flight Mach number is high or high subsonic. And the reason we had mentioned was that the propellers tend to go supersonic, which produces a low propulsive or a propeller efficiency. The turbofans, on the other hand, has a good propulsive efficiency only at high values. Now, turbofans, as I mentioned, is a mix between pure turbojet and a certain aspect of turboprop or a propeller, and a fan is essentially somewhere in between a propeller and a pure compressor, and the size of the fan is such that it is somewhere in between in terms of size. And as a result, in a turbofan, as I mentioned in the previous slide, it operates with a high mass flow through the fans and produces a high propulsive thrust, and a small mass flow as a jet and produces a low propulsive thrust, and combination of the two gives us turbofans which are generally of higher propulsive efficiency. And as a result of which, these turbofans become more and more competitive at a higher mass flow, and at a high subsonic mass flow, these turbofans are clearly the more efficient and more desirable propulsive devices, and that is the reason why most of the aircraft today fly with turbofan engines. The turbojets, or often referred to as the pure jets, operate with, as we have seen, rather low propulsive efficiency. However, as we can see here, when you need very compact engine, especially in very high speed aircraft, you do not have a choice but to go for the compactness of the engine, because the turbofans and the turboprops, they tend to be very large in size. And when the size is really the most important thing, you have to have a very small sized engine, quite often to be put inside an aircraft. In a supersonic aircraft, you need turbojets. So, when the Mach number of the flight is clearly more than 1 in supersonic aircraft, the choice often goes back to the turbojets or pure jets, in which you can get substantial amount of thrust in a compact engine. However, let us remember, their propulsive efficiencies are never going to be very good. So, in case of supersonic aircraft, we consciously go for turbojet engines because of their compactness, knowing fully well their propulsive efficiencies are going to be somewhat on the lower side in comparison to the other kinds of propulsive devices, which are the turbofans and the turboprops, which, as I mentioned, are often used in the lower Mach number ranges. Let us look at various kinds of jet engines that are operational today in various kinds of aircraft. As we look at these various kinds of jet engines, we shall be able to identify them for what kind of aircraft they are used these days. The first one that we have here is a very simple single spool bypass turbojet engine. Now, this operates on the principle that we have talked about. It has a compressor, and in this particular case it has a larger compressor and a smaller compressor. So, it has two sets of compressors on a single shaft, and the two sets essentially do two slightly different functions. In the first set, which sometimes people would like to call as fans, air goes through them, experiences compression, and then gets split up in two parts. The outer part, which is often referred to as bypass, and henceforth we shall also refer to that as bypass flow, and then this bypass flow actually goes over here, bypasses the entire engine, inner engine, and that is why it is called bypass flow. It bypasses the entire inner engine and comes out towards the rear, whereas a certain amount of flow goes through the inner compressor or the smaller compressors, let us say, gets compressed further. So, at the end of this process, it has undergone a large amount of compression, and then this highly compressed air is now taken inside the combustion chamber and then goes through the turbines, which extracts the work, and after this the hot gas and still highly compressed gas comes out from here, and over here the cold bypass air and the hot gas mix up, and then this mixture, certain amount of length is given for them to mix properly, and then this mixture of hot and cold, which is finally exited from the exhaust nozzle. This is not so hot anymore, and it is not so hot, not so cold, and a medium temperature gas now exhausts from this nozzle, producing a net change of momentum across this entire device, which of course, as we know, produces the thrust. So, this is the simplest form of bypass engine that came into being when it was realized that you could have a cold bypass engine and you could get some benefit out of the fact that certain amount of mass can be used to get thrust in a higher propulsive efficiency. The concept of propulsive efficiency has been brought into the picture, that this bypass mass undergoes a small change in the energy, and then this energy essentially produces a very small change in the thrust. However, here what we get is a mixed up thrust production. If we consider the bypass as a separate entity, it would actually produce, it is in the process of producing by the time it is here, thrust in a higher propulsive efficiency. So, the combination when it comes out actually produces a thrust which is of a higher propulsive efficiency than if it had been a pure jet engine, which would have had a higher exhaust velocity, which means it would have had a higher temperature and higher kinetic energy at the exit, and as I mentioned, this higher kinetic energy would have been a complete loss. Now, the kinetic energy exhausting from here is of a lower value, and as a result the amount of energy that is going out, and that we can say is a lost cause, is of a lower magnitude, and hence the propulsive efficiency of this bypass engine is of a higher value than a pure turbojet engine. And that is the reason why most of the engines today tend to be bypass engines. This of course, is what we call a turboprop engine, where one utilizes a gas turbine engine, as we are talking about, to drive a propeller. Now, propeller by now is our old friend. Propellers have been flying aircraft for last more than 100 years, 107 years to be exact as of today, and as a result of which they are useful devices, and as we have seen from the propulsive efficiency point of view, propellers are indeed the more efficient propulsive device within a certain flight Mach number. And now, as a result of which the propellers continue to be used in low flight Mach number aircraft. However, the rise of gas turbine engines has given us the option. The propellers can now be driven by gas turbine engines, which means you have air coming in over here, going through the process of compressor, combustion chamber, turbine, and then it produces a power, separate power through this shaft. In a, let us say, we can split the turbine in two sets. One set is over here, which drives the compressor, supplies power to the compressor. There is another set over here, which produces a very large amount of power, and then this drives this shaft, central shaft, and runs the propeller through this gearbox. And as a result of which, this is what we call a twin spool engine. It has two shafts, two concentric shafts, one which runs the basic engine comprising of the compressor, combustion chamber, and the turbine. Some people call it the core engine, and the outer turbine, or often referred to as the LP turbine, a low pressure turbine operating at somewhat lower pressure than the HP turbine, which operates at higher pressure. This runs only this shaft, and this shaft runs the propeller, and the propeller produces the thrust or main thrust. In case of turboprop engine, propeller produces as much as 85% of the thrust, 85 to 90% of the thrust. A very small amount of thrust may be available through the jet that is coming out in the form of exhaust jet, and this produces a very small amount of thrust. In this engine, the way it is designed right from the beginning, the jet thrust that is available here, and as we know now, this will be produced with a very rather small propulsive efficiency, and this is going to be very small, whereas the large thrust that is produced by the propeller would be produced with a very high propulsive efficiency. A combination of these two is going to give you the total thrust that is produced by a typical turboprop engine. So, remember, in a turboprop engine, propeller produces the large thrust, 80 to 90% of the thrust most of the time, and the jet that you see here produces only a very small portion of the thrust, typically 10 to 15%, very rarely more than that. Now, we can look at a little more of the bypass twin spool engine. This is, as opposed to the earlier bypass engine, a twin spool engine, which means it now has two shafts. Spool, of course, refers to the shafts. It is an old terminology which people have used over the years, and it refers to two shafts. Typically, the two shafts are concentric. There is the inner shaft which runs through, and there is the outer shaft which normally is used to drive the core engine, which comprises the one turbine, which is the HP turbine, one set of compressors which is referred to as the HP compressor, and hence this spool is referred to as high pressure spool or HP spool, whereas the inner concentric shaft which runs right through is run through the low pressure turbine, which is a set of turbines quite often, and which powers through this shaft this big fan and sometimes a small compressor over here. Okay. So, this produces a large amount of power, and it is often referred to as the low pressure spool. So, this mechanical arrangement that people have devised essentially creates two mechanical arrangements, one which is the low pressure arrangement, another which is the high pressure arrangement, two mechanical arrangement. Now, this allows us essentially to run the two spools at two different rotating speeds or RPMs, as a result of which most of the engines today, the HP spool runs at a higher RPM and the LP spool runs at much lower RPM. The reason for which we shall come to know as we go along. And as a result of this independence of the two spools, the designer now has the flexibility to design the two spools in a manner such that they independently operate at their best and most efficient operating condition. One can well imagine, and as we will go more and more, you would probably become familiar with these components, and you would realize that this independence is very important for operating each of them at their best efficient operating conditions. There are a few other components that are very important for the efficient operation of a jet engine. The first thing is, as I mentioned earlier, every such jet engine has an intake. Now, this is the kind of intake that all jet engines would have, and flow comes in through it, and hence it is called an intake. Now, design of this intake is a very intricate affair, it is not simple, and this shape of the intake over here, often referred to as cowling, is very important for the aerodynamic efficiency of the operation of this jet engine when it is flying with an aircraft. In a high speed aircraft, the design of this cowling appears in a very important issue, and it appears in the design right in the beginning, and it is a very long drawn out affair. The entire outer surface of the engine needs to be appropriately designed. As you remember, quite often in many of this aircraft that you may have seen, this engine is seen to be hanging outside the aircraft, quite often hanging from the wings, and this entire outer surface is open to the air that is flowing. So, certain amount of air is coming in, and that is going through the propulsive device to give you a jet which creates a thrust. There is a certain amount of air that is going outside, flowing over the surface, and this air actually produces drag that is additive to the drag of the aircraft itself. And remember, the thrust that is produced by this engine would have to overcome this drag for the aircraft to fly. Now, the engine designer has a job to make sure that the engine itself does not produce a large amount of drag, and hence the outer shape over here, and quite specifically over here, is often referred to as boat tail shape, and this ensures that the external flow over this propulsive device does not produce a large amount of drag, which, as you know, would have to be overcome by the thrust produced by this itself. Now, towards the exit of this propulsive device, as we have seen, we have a cold bypass flow in this bypass engine, and we have a hot inner flow or a core flow, and then there is a mixing over here. This mixing needs to be done very uniformly, so that the jet that comes out has a uniform temperature and pressure at the exit face. Now, this is very important, and hence the design of this nozzle system over here, all the way from here, the shaping over here is extremely important in terms of aerodynamics and the gas dynamics, because at the exit face right over here, we want absolutely uniform temperature and pressure profile, because if the pressure profile is not uniform, remember, the thrust that is produced is not going to be a linear or a thrust in the direction of the jet, but it will be a thrust produced which will have all kinds of components, sidewise or upwards or downwards components, which will render the aircraft movement in the flight in various kinds of directions. As a result, the aircraft will tend to have motions which could be a pitching motion, which could be a yawing motion, because the jet that is coming out here is not uniform and is not producing thrust that is unidirectional, but producing multidirectional thrust. So, the flow here needs to be extremely uniform as it is going out, and hence the design of these components here is of great importance. Some of these things we will probably talk about more and more as we go along. The next kind of engine that we are looking at is high bypass engine, as we have seen from the propulsive efficiency concept, that the higher the bypass flow, higher the mass of activation, more is the propulsive efficiency. So, we now know that this bypass flow acts in a manner that produces high propulsive efficiency thrust, whereas the inner flow produces a low propulsive efficiency jet thrust. So, more and more aircraft engines are being produced today, which have high bypass flow and comparatively lesser amount of inner flow. This has a huge big fan, and as we go along we shall see that these fans are getting bigger and bigger. This is ultra high bypass twin spool. The fan has gone bigger and its size is now substantially bigger than the core engine. So much so that the fan needs to be run at a lower RPM, and quite often they come with a gearbox. This gearbox is reminiscent of the gearbox that is used in propellers. So, it is almost becoming the size of a propeller, hence you need a gearbox to run this fan at a somewhat lower RPM, so that they are mechanically and aerodynamically quite efficient and produces a thrust of a very high order through the bypass, and as a result the overall propulsive efficiency now would be very high. This is a 3-spool bypass. Now, it has 3 spools. The inner shaft goes right through, runs only the fan. We have a intermediate pressure compressor that runs through an intermediate shaft spool, and then of course, you have the HP spool, which is the outer spool. So, you have 3 shaft arrangement, and some of the modern engines today do have these 3 spool arrangement. It gives the designer the independence of running 3 spools at 3 different rotating speeds or RPMs and design them accordingly. This is a kind of engine that is used normally in flying helicopters, and these are called turboshaft engine. This is a typical 2-spool turboshaft engine. These are used for running the propellers or the rotors of often a helicopter. This is a twin spool power plant, a variant of gas turbine engine often used in land based gas turbine, in which intercooling is used. That means, between 2 sets of compressor, the air is cooled down and then again compressed, okay, and this intercooling, as we shall see later on through the process of thermodynamics, produces a higher efficiency of the entire jet engine, entire engine, and this higher efficiency of the engine is often used in various power plants. More specifically, at this moment they are used in many of the gas turbine land based power plants with high efficiency operation. This is a kind of modern engine that is being designed today and likely to fly very soon, and it is a 3-spool combination of engines, where the main engine is 2-spool. The 3rd spool comes out from here, from this set of turbines, and runs the big fans, which are now referred to as prop fans, and these 2 prop fans have 2 gearboxes. So, that in some of the modern engines, the second prop fan actually runs opposite in direction, in rotational direction to the first fan, and hence they are referred to as contra-rotating prop fans. They are behind the engine, so they are often referred to as aft fans. So, these are the kinds of devices that are likely to fly very soon with various kinds of aircraft. This is the aft fan, in which the fan is at the rear, which is mounted actually on the turbines. Okay. So, the turbines are directly running the fan. You do not have a shaft here, and as a result of which the transmission efficiency here is almost 100%. There is no shaft. This is a 2-spool arrangement. This is virtually the 3rd shaft or 3rd spool, which are running independently of these 2 spools. This is a frontal view of a geared 2-spool very high bypass turbofan engine that is already being flown, and you can see that the fan sizes are huge. The size of this is huge. Each blade here is probably of the size of a full grown human being. This is a twin rotor aft fan that is in test bed, is being tested, and as you can see here the twin aft prop fans, and this is undergoing test. This is a picture in which the twin rotor aft prop fan is undergoing flight testing, actually mounted on aircraft. So, as I mentioned, some of these engines or flying devices you would be able to see very shortly flying all around the world. We can say that at the end that the various engine development over the years that has taken place has produced more and more fuel efficient engine that starts with the high propulsive efficiency. They also are tending to be more and more compact with the various kinds of mechanical designs that are possible, and as a result of which the thrust to weight ratio, which is the final measure of their utility value for aircraft engine, is becoming higher and higher. The research that is going on these days tends to look at some of the new issues. We would need to have energy audit and search for new fuels in the coming years. We would need to have engines that create less of pollution. We would need to have engines that create less of noise, and there are lots of regulations in place these days about noise, about pollution, and unless the engines actually conform to those regulations, they cannot actually be used or flown. For military aircraft, there is an additional requirement that quite often they need to have infrared signature devices, which would need to be installed in the engine. So, these are the various kinds of directions in which the engines are developing these days. We shall later on in this course, we will also have a look at the space propulsion devices, which would be coming towards the end of this course, and which will discuss some of these kinds of crafts which and the engines which power these kinds of crafts. So, the various kinds of propulsive devices that power various kinds of engines, the aircraft, especially the aircraft we had look at today, and as we go along we will have look at the science of some of these devices in the form of thermodynamics, in the form of aerodynamics, and various other sciences that are required to understand how these various engines actually work and produce the thrust that fly various kinds of aircraft.